In ideal MOSFET, the current between drain to source cannot flow when gate bias is below than threshold voltage. But in real MOSFET, there is a current leakage between subthreshold subthreshold region. The amount of current is low, but the change of the current at subthreshold is very large. It changes exponentially. So we're gonna look in a log scale. The reason that current leakage is the electron can exist in channel even if gate bias is larger than the threshold voltage. So the difference between source side and difference between current difference between carrier concentration between source and drain. So there is a diffusion current. So we want to be a current flow to be ideal. So which means below the threshold voltage, there could be no current flow in drain to source. After the threshold voltage, there could be current to be saturated as soon as possible. So we're gonna use a parameter of swing, which means how much gate bias needed to drive a 10 times more current. So in here, the swing can be defined as ratio between log scale ID and difference of gate bias. So as swing gets higher, then the slope gets lower. In same device, if we want to be a check a swing, then the formula will be 2.3 product ideal factor n product kVt over q. Now we're gonna find what causes subthreshold swing. First of all, the inner trap. The inner trap caused by a different property of oxide and silicon. In silicon is there is a crystalline state, but the oxide is amorphous state. So if we fabricate silicon on oxide, then the surface cannot exist in crystalline state. So the electrons trapped in to the channel surface. We say that this dangling bond. So as trapped electron gets higher, as gate bias goes up, then the trapped electrons will be larger. So it can affect as another capacitance between oxide capacitance and depletion capacitance. The equivalent circuit of explaining this situation is that inner trap capacitance is parallel to depletion capacitance. So the voltage applied to the channel is we can use this formula as the capacitance will be act as voltage divider between gate and channel. So we're gonna define that the how well affected channel voltage by changing gate voltage. We'll call it a coupling of VG, VCH. So as we said, to look for by changing a VG, then affected to VCH, we're gonna use this voltage divider thing. If we calculate this voltage divider formula, then there will be two types. If there is no trap, there will be the coupling will be affected to be ratio to between oxide capacitance and depletion capacitance. And if there is a trap occurs, there's another capacitance is parallel to the depletion capacitance. So we can express like here. And if the capacitance of oxide is sufficiently larger than the depletion capacitance, we'll call it the ideal state. And with using this n, which is ideal factor, if we calculate the subthreshold swing, there will be a 60 millivolt per decade. We call it a Boltzmann limit. In room temperature, the IDVG characteristic, the swing cannot be smaller than the Boltzmann limit. And there is another cause of a subthreshold swing is that a short channel effect. There is a Mosfet, typical Mosfet device, and below that, there is an energy band diagram. If we give more VDS or shorten the channel, there will be gap between the depletion region on the substrate side will be get closer. As we give more VDS or shorten the channel, then the overlap depletion occurs. The effects of overlap depletion is that if we look at this difference between Fermi level and gate size work function, there is no channel. There should not be channel induced. But however, as depletions get overlapped here, there is a reverse bias to the PN junction of drain side. So there is a slope between them. If there is slope, then that will be have a that will be result to the channel. So the current can be get through to the drain to source. We call it a punch through. So if we check the IDVG characteristics, we're gonna case it by here, case 1, 2, and 3. So as channel length gets shortened, then the punch through effect comes up. To solution to punch through, first, the reason because punch through occurs is that depletion regions get overlapped. So we're gonna increase the substrate doping. To reduce the depletion length, then so we're gonna dope more acceptors on substrate. Then so the depletion length gets smaller, then the depletion overlap cannot occur. However, there is a if we more dope the acceptor, which means there is a lot of more fixed charge than the by this fixed charge there can be there is more Coulomb scattering than the so it will be result a lower mobility than the driving current will get smaller. However, and if gate bias gets negative voltage, then the uh, reverse current can be leaked. So at the negative voltage, so at off state, current leakage also happen. And there's another reason, another difficulty is that if we give more dopant, then the uh, depletion charge will be increased, and it will be cause more junction leakage, and it results the generation, the combination, and tunneling effect. Because of a steeper energy band, there will be a lot of voltage drop, which causes a higher electric field. And there is another solution, is silicon on insulator. On normal FET, we will be fabricate oxide under the substrate. The swing will be get better. However, as the physical channel cross-section area gets reduced, then they will affect as more resistance, because the definition of current is product of area and current density. And there is another problem. So it is advantage that it removes the cause of the depletion overlap. However, there is self-heating problem. As I said, there is no junction leakage, then it is good, but the cross sections areas gets reduced, so there's more resistance. If we have more resistance, then the more heat will be exhausted. However, oxide blocks the heat exertion, then the temperature of silicon will be self-heated. Then if silicon gets heated, then the mobility of silicon gets lowered because of phonon scattering. Lastly, there is a strain relaxed buffers. We're gonna use a substrate with two different materials, which means a different energy band gap. We use a germanium in the channel side, set channel surface, and the substrate side we use a silicon. Energy band gap of germanium is half of silicon, so there is a band offset which can work as buffers, as depletion overlap occurs, the silicon will be silicon band will be goes higher, which can be affected as a buffer. However, if we try to use these structures in normal state, at inversion state, it affects negatively, which means at inversion state, electrons should be induced to the channel surface. However, the band offsets affects reversed, so it blocks the electron movement. And to fabricate these strain relaxed buffers, we need to be a germanium to be nanoscaled, because to use quantum Weld effect, it should be a nanoscaled, which means it is harder to fabricate, and there will be defects will be goes up, which means yield per die will be go lower, and also cost per die will be go up. The complementary MOSFET, which is CMOS, is consistent with a NMOS and PMOS. We use CMOS as inverter, which means if the input is at logical high state, then the output will be logical low state, which inverts the input. So if we draw this input-output graph, voltage of input-output graph, like here in IDEA, which we try to use IDEA switch, will be at middle side, form like a unit step function. So each state between this graph, at the input high state, input low state, there will be output will be high. So the PMOS will be get turned on and the NMOS gets turned off. As input voltage gets higher, then the NFET will be saturated and PFET will be in linear state. At the middle, both MOSFETs get saturated and turned on. And as input voltage gets logical high, goes to logical high, then the MFET turned on and PFET turned off. So if we draw these two devices and one graph, we will look like here. The yellow line is the input-output voltage characteristic, as we saw before, and we can see that the crossing point between PFET and MFET is how is really is Q point of MOSFET. So we want to be reduce this middle stage, which is both MOSFETs are turned on. Then the current flowing to the ground, the power exertion will be high. So to reduce these both times, we're gonna match two devices, which means that we're gonna match these two devices with same material property. if we define this P set and set time as tau, there will be total resistance and total capacitance. To reduce the P set and set time, we have to reduce the resistance and capacitance. So because of difference between mobility of electron holes, there will be not same as really same material property. So we're gonna modulate this device length and width. The ratio between two width at saturation region is doubled at long channel, which we see like here. And as the channel length gets shortened, there's no different because of difference between channel width. So we needed to find another solutions. And there is a IDVD characteristic of between two MOSFETs. The ultimate goal is that to match this threshold voltage to operate at same time at saturation region. So it is to get lower this difference and match this swing. So in actual response will be like here. The output cannot follow as fast as input. So in the voltage, we define this TDF, which means VD is output voltage is half of input voltage at the time, and the TDR, which means rising time. And if we draw this current state, will be like here. At first, here, as falling state, then the MFET will be turned on. Between the TDF, at the time, the NFET and PFET will be turned on at the same time. And at the rising time, the PFET will be turned on, turned off. So the TDR, at the TDR, both MOSFETs get turned on. So at the TDR and TDF, the current flows directly to the ground. There is no current flow to the load capacitor. So if we calculate this energy per cycle, like here, and if we calculate this dynamic power dissipation during cycle, is that product with the energy with frequency, which means a duration between whole cycle. So we can, using this, we can find this total time of delay is here. The total delay time is affected with the load capacitance and effective resistance of both MOSFETs. So our goal is that to reduce this delay time T. In integrated circuit, there is a lot of logic gates on output node, one output node. So which causes the more capacitance to the more capacitance, and that leads to the more delayed time, which causes more power consumptions because of uh, the TDF and TDR gets higher, gets longer, and the both MOSFETs are turned on, and also that causes a slower response time.